Knowing the hydronium ion concentration, or H3O+, is necessary in many different instances. But since the values for the hydronium ion concentration are so very small, with negative powers of 10, the pH scale is used more often to conveniently report the acid concentration. So the pH scale is on a scale that's based on the numbers from 0 to 14. And to calculate pH, we use a logarithmic scale, and pH is equal to the negative, don't forget the negative log, of the hydronium ion concentration. If you rearrange this equation, we get a second equation that allows you to calculate the acid concentration when you know pH. And we'll do examples for each one of these calculations. But let's get a little bit better idea about the pH scale and what it tells us. So when we're looking at the pH scale, the pH of 7 is neutral. So if the scale goes from 0 to 14, in the middle is the neutral solution. A pH that is greater than 7 is considered to be a basic solution. The closer it is to 7, it would be slightly basic, and it can range to very basic, but anything but bigger than 7 is basic. And pH values that are less than 7 are considered to be acidic. pH is convenient to measure. We can use what's called pH paper. And pH paper is soaked in chemicals called indicators, and these indicators change color depending on what the acidity of the solution is. There's also a digital meter called a pH meter, which gives you digital readouts once it's calibrated to determine what the pH of the solution would be. So one of the things that we have to be able to do is to convert an acid concentration into a pH. To do this, we use our calculators along with the equation that pH is equal to the negative log, it's log base 10, of the acid concentration. So let's look at letter A. So we would say pH is equal to the negative log of 1 times 10 to the negative 6. And plugging this into your calculator, you would find that the answer is 6. Now, if you have trouble entering this into your calculator, I encourage you to come by and see me, or stop and talk to the math tutors and they can help you enter it into your calculator. For most calculators, you would simply enter in negative and then find the log, the log base 10, and then enter in the number. If when you hit the log button you get an error, then you would enter this in reverse order, which means you would enter in the number, then the log, and then the negative. I'd be happy to go over how you enter logs into your calculator. Now, one thing on this letter A example, which is kind of interesting, is that we notice that the exponent here is equal to what the pH is. It's the positive value of the exponent. This will always be true when your coefficient is 1. So anytime the coefficient is 1, know that the pH is the positive value of the exponent. A pH of 6 would be considered an acidic solution. In fact, a pH of 6 has 10 times more acid than a pH of 7. 1 unit of pH, because it's a log base 10, has a 10 times change in acid or base concentration. So for example, from a 4 to a 5, a 4 has 10 times more acid than a 5. If I had a 4 to a 6, well, this would be 100 times more acid in a 4. Because each change in pH gives you a change of acid concentration by an amount of 10 times. Now let's take a look at the next problem. This one doesn't have a 1, so I wouldn't easily be able to just write the answer down. I do, however, know that when this coefficient is not a 1, that my exponent, the number, is going to start with 11. It will always be 1 less than whatever the exponent. Let me show you. So pH equals the negative log of the acid concentration. So now we need to plug this into our computer, our calculators. And I get I have to put the positive, sorry. I get 11.3279. Now this is what I was talking about. And this will be true. We'll look at it on the next problem. When the coefficient is not a 1, I still can kind of begin to predict or know if I'm getting it right, because the first part of my pH will always be 1 less than the exponent. Now my second thing would be, how do I know how many decimal places to go out? The convention with pH is it's dependent on your coefficient. So if you have 2 digits in your coefficient, then you will keep 2 decimals. So this number I would report as 11.32. Now this pH is greater than 7. So a pH greater than 7 would be a basic solution. And so finally the last one, let's calculate. So pH is equal to the negative log of the acid concentration, which is 6.21 times 10 to the negative 3. So now I plug this into my calculator. And I get that the pH is 2.2069. Now this is what I was talking about. You see how this is not 1, and so my first number is 1 less than the exponent. So I knew this was going to be 2 point something. So I have 2.2069. I have 3 digits in my coefficient, so I'm going to keep the 2, the 0, and the 6 and cross out this. So I get 2.207 for my pH. And this pH is less than 7, so this solution would be acidic. Now we have another equation that allows us, well, it's not another equation. Let me rephrase that. When we rearrange our equation to solve for pH, to solve for the acid concentration, we get the acid concentration equals 10 to the negative pH. And so given the pH, we can solve for the acid concentration. So on letter A, I would say that the acid concentration is equal to 10 to the negative 10.2. Now I can't have decimals in my exponents, so plugging this into my calculator, I get that this would be 6 times 10 to the negative 11. So the acid is 6 times 10 to the negative 11. I chose to only use one coefficient because there was only one digit past the decimal, which tells me how many digits in the coefficient. That's a little bit confusing, that convention. So I don't want you to get so caught up in that convention that you can't do your calculator correctly. So first practice the calculations and then try to process some of that other stuff. I would look at pH, and this is a basic solution. We see here that the concentration is less than 10 to the negative 7 of the acid, so that makes it basic as well. So for the second one, H3O plus is equal to 10 to the negative 5.8. So 5.8. And I get this answer to be, I have 1.58 times 10 to the negative 6. If I wanted to look here, this has only one past the decimal, so I think I would write 2 times 10 to the negative 6 if I was following the convention. This guy here is acidic. And that makes sense because the concentration is also greater than 10 to the negative 7. And finally, this last one, when it's a whole number, you do not need to enter it in. It would just be 10 to the negative 7. As long as it's a whole number, that would be a fine answer. And this is actually a neutral solution. Now in this last problem, I want to show you one other thing. So pH, remember, is equal to the negative log of the acid concentration. Now be very careful. In this example, you were given the base, so I can't just plug it in. That actually would calculate something called pOH. So if you're given the base, like in this example, we can go back to the equation we used with Kw, where we know that 1 times 10 to the negative 14 is equal to the base concentration times the acid concentration. So if you're given the base, since pH is based on the acid concentration, you have to calculate the acid concentration first. So plugging in the numbers, I get 1 times 10 to the negative 14 over 2.43 times 10 to the negative 11 equals the acid concentration. Let me plug that into my calculator. And I get the 3, I'll say, I get 4.115, so 4.12 times 10 to the negative 4 is my acid concentration. So this is what I'm going to use to calculate the pH. So I guess I wanted to point this out just so you read your problems carefully. So now I can say pH equals the negative log of the acid concentration. So pH equals the negative log of 4.12 times 10 to the negative 4. So I have, plugging it into my calculator, I get, and I'm going to do to 3 past the decimal, I would say 3.385 equals my pH. So this solution, from the pH, I could tell you that this solution would be an acidic solution.